G'day everyone, and welcome to today's seminar. So today we're going to be covering roof bracing design and installation. So if we just start off, who am I? I'm the engineering manager for Prida Australia, so I've been with Prida for about 19 years, and I run the engineering teams in Australia and New Zealand. And really my core focus is to promote and educate efficient engineering design and compliance requirements to our customers and their builders. So that's really the purpose of today's presentation. Who's Prida, if you don't already know? We form part of a business called ITW, which has got a broad range of recognisable Australian building names. Our core market is timber roof, floor trusses and wall frames. So we provide engineering design software, technical support, frame and truss manufacturing equipment, and we also manufacture an extensive range of steel timber connectors and structural brackets for building projects and for also DIY and outdoor structures. Okay, so today's presentation, we're going to cover four main areas. So the first part is really just understanding a bit about roof bracing methodology and design. And then we're going to move on to some common site fixing requirements for roof bracing. And then we're going to look at some things outside of 4440, which is some different geometric truss shapes and how to brace them, and then look at some common site installation issues at the end of the presentation. So if we look at the legislative requirements first, the building and design or installation of trusses is governed by 4440. It's called up in the National Construction Code, and it's a standard that governs timber roof trusses, timber nail plated roof trusses. So covers certain building classes, class 1, 2, 3 and 10, and also light commercial. You can use it to get some bracing designs for light commercial structures. What are the scope limitations? These are sort of key things to keep an eye on, because outside of these scope limitations you normally need some engineering guidance. So the 4440 has these sort of spelt out in the application of the document. The maximum roof pitch is 45 degrees, so you try and keep the pitch or the bracing below those levels. If you get trusses outside of that, it's always a good idea to source engineering advice. Maximum truss span of 16 metres. Once you start getting longer span trusses, the compression loads and the cords build up, and so there's a cut-off point at 16 metres for the application of 4440. Truss spacing, so 900mm for tile roofs or 1200 metres for sheet roofs in N3 or lower. And the reason that is as well, wider the truss spacings are, the more load it has to carry, the higher the compression forces are in the cords, and the more attention needs to be paid to the bracing and application. And you're not allowed to use it in snow-loaded areas. So again, seek engineering guidance when you have those sorts of situations, because snow loads can be quite high forces that are applied to the building. It could be anywhere from 100 kilos a square metre to 250 and higher. So again, these create substantial compression loads in the cords, and there needs to be a little bit more attention to detail for the bracing in those types of buildings. So if we just move on to roof bracing methodology and design. So the two primary functions of roof bracing is really to resist the buckling forces in the truss cords and to resist the wind loads on the roof structure. So we're going to look at both of those in a little bit more detail in the next few slides. Buckling forces. So when you subject a member to compression, it will tend to buckle in the direction of the narrowest width of the member. Okay, so the more slender a member is, the more susceptible it is to buckling. So as you can imagine, with trusses, they're all made of sort of 35mm wide material, so they're actually quite prone to buckling. Okay, and a good illustration of a buckling in action is when you get a ruler and you press it on the end. The tendency for it to push out sideways in the direction of the narrowest width is buckling in action. Okay, so when a member buckles, it generates a force, a lateral force, and that needs to be resisted by the bracing system, and that's one of the primary functions of roof bracing. So if we look at a typical truss, normally in the top cords you have these large compression forces, and normally in the bottom cords you have a tension force. Okay, so those forces need to be resisted. You get the opposite for wind uplift. Okay, so even though you've got compression forces normally in the top cords and tension in the bottom cords, when you get a higher wind uplift, that can actually reverse. So you can actually get high compression forces in the bottom chord and high tension forces in the top chord. And also a real key thing to keep an eye on is long webs. So again, slender members, webs, they're subject to compression forces, and sometimes when they get long enough, they may need a buckling restraint, which is either a mid-height tie or some stiffening to make sure they don't buckle and fail. Okay. So the way that the members in a roof truss system work, once a compression force is applied, the restraint system that's provided really comes through from the battens. Okay, so you can see here, these battens have to be strong enough to be able to resist the buckling forces that are applied. But these sorts of loads that are generated, so if we look at a 10 kilonewton compression force in this member, there's a formula in 1720 down here to generate or calculate the amount of buckling force that are directed through these members. Okay, and it's important to note these buckling forces could go in either direction, so it needs to be restrained in both directions. Another key consideration is that these forces are generally cumulative. Okay, so you may get the situation where these trusses are all buckling in the same direction, and the buckling forces are added up for each one of the trusses in the direction of the run of those trusses. Okay, so as you can see here, the buckling forces are applied to the battens. We've got the battens fixed on here, and these forces transfer through the battens, and then when they reach the speed brace, they get redirected out to the external wall. So you can see here, these two bits of speed brace, the buckling forces in this direction are taken out to these external walls. The wind loads. So we've talked a bit about buckling. Now we'll move on to the wind loads on the structure. So part of the application of roof bracing is really to resist the buckling forces, and the other part is to resist the lateral wind loads on the building. So you can see here the horizontal wind loads on the roof structure. Part of that comes down into the ceiling diaphragm, and then from the upper part of the wall also it comes up into the ceiling diaphragm. Then the top part of this part of the roof gets resisted by the speed brace. Okay, so if you see this in application, this is the projected area for a normal type truss calculated, and this force with the wind pressure gets resisted by the bracing on the top chord. Okay, so most of the load goes actually through the ceiling diaphragm. So this sort of portion down under here comes in through the ceiling diaphragm, and that's stabilised by plasterboard. Okay, so the plasterboard sits on the bottom chords of the trusses. If it's fixed direct, that provides the bracing system for the truss at the ceiling diaphragm level. Okay, so the top chord bracing up here is purely for this part, the shaded part of the load, which comes through the top of the roof. And again, mono trusses tend to have slightly higher loads based on the span because you don't get the reduced area. It keeps increasing as the truss increases in depth. So you may get slightly higher wind forces on a mono truss. And again, ones with stub ends increase it again as well because you've got that depth, the starting depth at the heel, which can increase the forces on the building. So really a key important point for roof bracing. Speed brace can only carry load in one direction, that's tension. Okay, it can't carry a load in compression. So it's important to always have speed brace installed in this cross sort of configuration to make sure that it can cater for wind loads from either direction. So as you can see here, wind direction coming from the left-hand side gets directed through the battens and then gets taken down by these two bracing runs out to the anchorage points, and these effectively become redundant for that wind direction. When it comes from the other way, then these two become redundant, and these two, once highlighted in red, become activated. Okay. And so with these speed brace, it's got to have a rigid anchorage point at one end. Okay, so usually this apex point isn't considered an anchorage point. It's where it hits a wall or a rigid point that is considered to be anchored. So if we have a look at some common types of bracing layouts, they can be varied. It would probably take another full session to cover common bracing layouts, but 4440 covers most of the common bracing types. It's fairly prescriptive and easy to follow in most cases. And for uncommon truss types, we'll cover a bit of that later on, but sometimes it may be an idea to seek engineering guidance if there's some complex truss shapes that may need some specialised bracing. But the 4440, pretty standard stuff. You've got your cross bracing in X's on both sides of the ridge line. The only change to that is really when it gets up to 13 meters, there's a requirement, because the wind forces and the buckling forces start to increase, to have these additional bracing bays established at 13-meter centres. They're generally single runs of speed bracing crosses with these solid compression nogging blocks. The key detail is really to make sure that where these bracing runs line up, that they line up on each side and you have the compression block directly running between them. Okay, and the main span of the trusses as well is also braced in the normal way, and it may be single or double based on the span of the truss, the wind loads, and the pitch of the roof. So sometimes you don't always have to brace every truss in a job. The ones that don't often require bracing, hip trusses, because they're braced by the supported creeper trusses coming in from each side. TGs and TSs generally don't require it, because you've got the horizontal top cord is restrained by the jack top cord flying over the top. Valley trusses, they basically sit on top of the standard trusses, so there's less buckling force in those particular members. So it's not often required to diagonally brace those. So the bracing usually runs on the underside of the valleys across the normal run of top trusses. Boomerang girders, again, they're braced by usually trusses coming in at equally spaced centres on each side. So there's not generally the requirement to brace those boomerang girders. So I'll just have a look at some of the site fixing details. These details are generally contained within the 4440. They're specific details that cover most of the connection types that are used on site. And again, we'll just reiterate that it's important to note that the speed brace has to have at least one minimum effective anchorage point to be compliant. So if we look at the first detail, the splice fixing, generally 3 common nails with a lap splice. So you just run the speed brace over the top of each other, fix through these 3 common holes. The other connection type is a wraparound splice. So it's just 2 nails through the top and then lapped on the side with 3 nails. Now the one key thing to note is these lap splices can only be used outside 2.5 meters away from the anchorage point. The reason being is that with trusses, as we said, compression in the top cords, as you go down towards the heel of the truss, these compression loads actually get higher. Okay, so this is a better connection type for splicing. And so generally the standard specifies that within 2.5 meters of this external wall that you should switch to this type of splice fixing. Apex of the truss, pretty standard detail. Again, the 2 nails and 3 nails down the side face. When you fix to wall plates, you've got to keep this angle. This is a real critical one, less than 45 degrees. You don't want the speed brace dropping too sharply here over the top of the truss. And again, 2 nails to the side of the top plate, wrap it underneath, and 3 nails on the underside. There's also some alternate fixing details for those types of connections. Here you can see one, which is a good one to use. It's basically the 2 nails, 3 nails down the side face, and then a compression block in between the trusses, and this compression block should be on the side of the truss where the speed brace is running. Okay, so you shouldn't have it on this side. It should be always on the direction in which the speed brace is running. And then you have 2 multi-grips fixed to each truss heel. And what happens is, as the load comes onto this truss heel, the truss heel will tend to try and rotate. And so that compression block just holds that truss heel in place and transfers the force into the wall plate. That's a really good connection detail for steel beams as well, because you don't have the opportunity with a steel beam to fix underneath the top plate, so you can put that type of fixing detail in place. End fixing, so you can also fix the bottom cords of girders because they've got girder brackets and truss boots which can take these loads from the bracing system and direct them into the bottom cord of the girder. Okay, so that's considered to be an anchorage point as well. Vertical bracing, another one that's commonly missed on site. When you've got cut-off trusses or mono trusses, you should have bays of cross bracing at the vertical ends of the trusses. And when you've got brickwork, another because you can't wrap it underneath and there's not enough fixings on this lower wall plate, you can install a 9045 timber block, fix it off with nails or screws, multi-grip each side, and then you've got enough fixing of nails on these edges of the blocks to be able to stabilize the connection. Cantilever bracing, generally you're only required to brace cantilevers greater than 1 meter, but these are the sorts of details the standard provides to run the bracing out and then back to the wall. So it directs those forces with this secondary bit of speed brace back into the wall. And again, you can see this compression block in place to direct it in the direction of the speed brace that's running to direct those loads into the wall. So if we look at some common different truss shapes and how to brace them, these are really the key thing to remember is when you're doing different geometric truss shapes is that each change in the plane of the roof truss needs to be stabilized. Okay, so if we look at a normal standard truss, you've got two bracing planes up to the apex and then down to the heel. So only two there. When you have a truncated or a top-hatted truss, now you've got three. Okay, so you've got this top plane that runs across the horizontal top chord, then down the other side, and most of the compression load goes through that blue line. Okay, it doesn't actually, top hat truss is just sitting on top. It's not doing much in terms of performance. All the loads come through this horizontal top chord, so you've got to make sure that that's stabilized adequately. So you can see here, you can see these bays of cross bracing across the horizontal top chord that run out and connect with these sloping top chord bracing links. So put the bracing in place, and then of course you need your battens on top of that to provide your buckling restraints, and then you sit your top hats on top. And the good idea is to just extend these overhangs on the valley trusses that you sit on top, so you've got a positive fixing between the valley truss and the truss underneath. The other thing we recommend highly with these types of connections is just to offset where the bracing runs lie, because if you try and tie all this into one truss, it gets a bit messy trying to nail and fix these. So if you just separate them with one truss apart and put a compression block in between there, that's usually the best application for these types of bracing runs. So you can see these compression blocks sitting at the intersection from where this horizontal top chord bracing meets the sloping top chord bracing on the outside. Cut off mono trusses, so we covered this before. So you can see bays of cross bracing at the high end, and if there was a stub end at this end, you'd have to have it at this end as well. And they generally meet at where the roof bracing intersects with the apex of the truss. Okay, so you've got one here, one there where you've got this cross bracing coming in, and then one at this end. So the bracing could get directly transferred into this vertical bracing at those high ends. And normally you'd have this compression block. There's only one shown here, but if you had it over, have this bay over 2 or 3 trusses, you'd have to compression block between these points where the vertical bracing is. So a continuous run of blocking between those points. And here you can see some typical applications of cut-off monos. If the cut-off mono is quite short, less than 300, you can just have 2 rows of solid blocking there and just brace out to the ends of the truss. If the stub end gets above sort of 350, 400, then you'll have to instigate this cross bracing at the wall. Okay, so some typical examples you can see from site: cross bracing in place as per the details. You can see one here with cross bracing all fixed off nicely, and another one here. Okay, so that's it in application. You can see the top chord speed braces coming in at the top here as well. And so that all goes in well. Where you want to avoid is these struts or missing bracing on these ends, because there's nothing there really to resist the pulling force that comes in from the brace on the top chord. Another common one which isn't in the standard is box gutters. Okay, so they're become really commonplace these days, and again it's this bracing each plane of the roof. So you can see the top chord plane, this vertical plane, and then the bottom chord plane. Okay, so you have to make sure that each one of those areas is adequately braced. So you can see the top chord's running in here, you've got compression blocking between, and then you've got this horizontal bracing at the underside of the bottom chord cove out to the wall. So the loads come in through the speed brace, directed through the compression block, and then back out to the wall. Okay, and you can see different heights. This one's less than 300 meters, so 300 millimeters, so you can get the compression blocking. When you've got 300 to 500, you can have 2 blocks and some bracing input. And then if you've got greater than 500 mil, again, you can run with this cross bracing with some blocking at the top and the bottom level. Some common site issues. So we can see a job here. It's critical to get these fixings right, because trusses are so slender that if you don't get these bracing systems correct, you can have catastrophic failures. So this was a job in Malaysia with a school, a military school, large span trusses. There was supposed to be an inauguration the next day after this happened, but fortunately there was no one in there when this collapse happened. But what was the instigator of this? As you can see, these horizontal top cords here with the top hat truss setting on top of it. They had battens in place, but they didn't have any bracing. Okay, so when it started buckling, it all started buckling in the one direction, and there was nothing there to resist it. So then it didn't have the speed brace in place, and it reached a stage where it just reached failure point, and the whole thing became a bunch of matchsticks. Cantilever bracing, as we mentioned, see this angle down here, it's just too sharp, it's too steep, and so the speed brace isn't very effective. So what you should try and do is either brace out to the ends and brace it back to the wall, so you'd have the bracing running out to this end here and then back into the wall. Or if it's less than 1 meter, you can also just run it over the top of the truss and run it down through the open space in the void here, and run it directly down out to the wall. That saves you having to hook down at this sharp angle. Just run it straight down onto the wall as long as your cantilever is less than 1 meter. Make sure you brace in both directions. So you can see a job here. I've got all the speed brace running in one direction. Okay, so if you've got a wind load from this way, everything's great. You've got a wind load from this direction, you're in a bit of trouble because it only, as we mentioned before, it only operates in tension. So all of these braces become ineffective once you've got a load from this direction. Use the correct end fixings. Okay, they're pretty specific, the details in 4440, and they cover most of the common applications. And so you just need to get these sight fixings right. Okay, just lagging it onto the top plate and one nail's not cutting the mustard. Sometimes you have conflicts, so you can't get underneath these top plates. So you can see some plywood in place, but then you have to adopt and switch to a different option. You can see the steel beam in place here as well, can't get underneath there. And so that's when this detail becomes applicable from 4440, where you just fix it onto the truss seal, put the compression block in place, 2 multi-grips, and that resolves those issues. You can also use a variation of that, which is this vertical bracing fixing. So you can fix a block between these trusses on flat, as long as you get enough nails down the side face. So you put another block in on top here and fix down the side face of those 2 blocks. So you'd have 3 nails in here and 2 nails in the block above, and then that's an adequate end fixing detail. So you can see another sight fixing, almost got everything right here. They've lapped it down, 2 nails, or they've got 3 nails in there. 3 nails down the side face, multi-grips here, multi-grips there. What they've missed is this compression block, okay, in the direction of the speed brace, so it should be going in between those 2 truss hills. Vertical bracing, as I said, it's often missed on site. So you can see a run of, cut-off trusses here. They've got the temporary bracing in place, but they've forgot the speed brace. So just need to make sure that on those run of cut-off trusses that you have at least a bay of speed brace vertically at least every 9 meters. Usually just try and start it at one end and put one at the other end, and then at intermediate 9 meter centers to make sure that it's all stable. So battens really critical. As we mentioned, the trusses are very slender members, and so compression forces, if these battens aren't fixed properly or fixed at all, these members, the top cords, can buckle and cause failure. Okay, so they're really critical to make sure these nail fixings are in place and fixed off properly. Another common issue when they used to use hardwood battens is end fixing near the ends. Hardwoods has a high tendency to split. So you can see these nails here towards the end of the batten, and they've just split through. And that was the cause of a roof collapse in South Australia a number of years back. It was up in place for 9 years. They fixed the roof battens. They terminated all the battens on the end of the girder, and the nail fixing was too close to the end. The batten split. Over time, the battens pulled out, and then eventually 9 years after it was installed, it collapsed and killed 3 people. Splices on top cords. So yeah, the standard requires you not to splice adjacent to each other, and only 1 in 3 batten splices on any one top cord. Okay, so that's applicable for all standard trusses. No splicing is allowed on girder trusses. Okay, so you're not allowed to splice on girders, and the battens have to be fixed to each ply of multiply laminated trusses. Of course, if you've got a multiply truss, it stands to reason you're going to have much higher compression forces and buckling forces. So you must have those fixings to each laminate, otherwise you run the risk of the cord actually shearing the nail off through the batten. So make sure they're in place. And you also need to make sure in these areas where you've got potentially parts of the top cord that are like in a Northlight situation, you need to make sure that you've got those buckling restraints still in place on these sections of the roof. Even though you may not have sheeting in there, you've got to make sure that those restraint mechanisms go in place and are fixed off properly, and the speed brace runs up into those areas as well. So as we mentioned, truncated girders, they need the jack trusses to be fixed directly to the horizontal top cord to restrain it. So you can see a number of photos from site from here. There's a huge gap between the jack top cord and the actual horizontal top cord of the girder. And so what happens is if you don't have that fixing in place, that mechanical fixing, that horizontal top cord is carrying a huge compression load, and over time it'll buckle sideways and eventually collapse. So you need to make sure that you have those systems in place, fix them off properly. You can see another photo here with big gaps between these two members. They need to be continuously restrained for the buckling of those top cords. And we touched on this previously, the web ties. So you can see here fabricators provided stickers on each one of these members saying, please brace me. They haven't gone in. And of course the webs have got this high compression force, and because they're so long and slender, they failed in buckling. So this is the detail from 4440, the typical web tie bracing schedule, which is basically a batten or a web tie that's run along the mid height of those webs, and then you have cross bracing running between the top and the bottom cords, and a bay of that in each one of these runs needs to be put in. If you have staggered web profiles and they're not all aligned, then you need to switch to another mechanism for stabilizing the webs, which would either be a T-stiffener or a side scab to the web. So those are other options, but this is the most efficient when you have a common run of web profiles. All the trusses are the same shape. This is the easiest and most effective, cheapest way to resolve those buckling issues for webs. That's the end of the presentation. Any questions?
So do the small cross braces, the X's on the 13-metre truss bracing, need to be doubled?
Sometimes they do, yeah. It depends on the truss band. So there's a set limit in 4440. It depends on the wind speed. So the higher the wind speed, the more critical it is to have cross bracing. Generally, the bays of bracing may not require it, and it's usually the top cord bracing that has the doubles. But yeah, it just depends on the type of job with those sorts of things. So I might just see if I can get the 4440 up here for you. I had a copy open before. So if we just scroll down here to the applicable section, so you can see it gives a table in 4440 with the wind speeds and the roof pitch. So below 20 degrees and up to N3, you can have single brace for 16 meters. Okay, and then once you start going to the higher wind speeds and these steeper roof pitches, you can see you get a reduction in the span, so they need to be doubled up. Okay, and these higher wind speed zones, yeah, the span length becomes reduced where you need to switch to double speed brace. Okay, you see here, generally I generally just brace those with single. Okay, and then that's these main run of speed brace through the main parts of the building that become potentially doubles.
I've got one more question. And what about really short trusses, e.g. a 500mm truss? Does it need to be braced?
No, generally not. There's actually our software warns users when, because it actually does a calculation on the length of the member and the compression force in it, and it'll tell the user if there's an issue with the buckling restraint on it. So it usually warns them prior to the job getting to site that there may be some special considerations for buckling, but normally if it's less than 500, unless you've got a really huge, where it can happen is really short or low girder trusses. So if you've got a really short top cord span, and what we generally recommend is there's actually a detail that we supply, which is putting nogging blocks in between the truss cords and then putting some short run of speed brace over those particular trusses. But in general, you know, a standard truss with a 500 mil length isn't going to generate enough force to be able to cause any issues. It's really girders, you know, highly loaded, low pitch girders that may need an occasional attention to detail. But that, like I said, generally gets flagged in the software, and they come to us and they'll ask us the question, and the fabricators will normally supply that on the layout to make sure that that's notified to the builder.
Actually, I have one more question about bracing details for layout. So the bracing details that you showed, are they available for detailers to put on layouts?
Yeah, they are. Generally, a lot of the detailers use those graphics and plug them onto their layout so that they're available. Yeah, so they are available to our fabricators for use on their layouts. Yeah, ceiling bracing. There's a question about ceiling bracing there from someone. Generally, what happens is with ceiling brace, the plasterboard actually provides that restraint mechanism for trusses. So as long as the plasterboard's fixed direct to the trusses, that provides the buckling restraint for wind uplift. When that mechanism gets removed, so if you have a suspended ceiling with furring channels and clips, all of a sudden you lose that buckling restraint for bottom chords, and then you need to find another mechanism to provide that restraint. Okay, so the standard actually has that specified in here, and I'll show you where it is. So you can see here, it's very similar to the roof bracing, and what you have to do is basically run it in these diagonals, and then the designer has to. So when you have those sorts of situations, you need to flag it with the fabricator, because they need to design the trusses with these restraint mechanisms that are different to plasterboard. Okay, so they might be bottom chord ties that run through the building, and so when you have those suspended ceilings, those need to be noted on the plan to make sure the designer is taking that into consideration when he's doing his truss designs. But that buckling restraint for the trusses is usually a similar mechanism to the roof bracing, except that it's applied on the bottom chord of the trusses. Okay. Now, one key thing to note is it's not a building stability detail. Okay, it's only to do with the buckling of the trusses. So once you get a suspended ceiling, as soon as that drops away, there needs to be another mechanism put in place, which is either wind trusses or some other diaphragm system to stabilize. And it's not the trusses, it's the walls. Okay, so when that wind load hits the walls, you need to, usually it gets directed through the plasterboard and out to the bracing walls. If you don't have that mechanism in place with like a suspended ceiling, then you need to substitute it with something else. Okay, so this bracing only takes the buckling forces from the trusses. It doesn't take the wind load like the roof bracing does. Okay, so that's the key distinction between those two. So you can see here the note in 16440, bottom chord ties and bracing details are intended only to laterally restrain the truss bottom chords and do not provide lateral stability to the building to resist lateral wind loads. And the reason is that most of the load gets directed in through the ceiling diaphragm. Okay, so the roof bracing takes a proportion of that loads. So when we looked at that area that's projected, the roof area is much smaller than the area that is captured by the ceiling diaphragm. So there's sometimes special attention required when you have suspended ceilings.
All right, looks like we've answered all the questions, Ian. So
cool.
Thanks for attending, and we'll see you next time.
Thanks, guys. Take care.